All right, so k-means is a wonderful, simple algorithm, and I think it's older than I am. I think they invented it in 1957. It is really simple and really effective. And this is unsupervised learning, where it's not, you don't have an answer and you're trying to predict the answer. You just have a bunch of data and you're just trying to cluster it into groups. So first we're going to make a data set with data to sort. And before we use just 2 Gaussian distributions, here we're going to use 5 Gaussian distributions to make a more interesting, complicated situation. And so see there's 5 central locations and there's various standard deviations. And so there you go. 3 tight clusters on the left and 2 dispersed clusters on the right. And we like to sort this into categories. And first we'll see how k-means works, and then we'll talk about how it works. So k-means, if we tell it that there are 5 clusters, you see it's the first line of this code is we told it to fit 5. It's actually pretty tough to decide how many clusters to use. But if we're willing to start with that data, then k-means will work pretty well. And all we do is this is what does it, we just fit it. And all the rest of this is just to plot it. So it's like the first 4 lines that do all the work. We create a default k-means machine and just run it. And the n init is the default, but it means it will actually try it 10 times over, starting from different initial states. Because as we'll see, one defect about k-means is if you start it with a bad starting value, it can get stuck in a non-optimal state and not converge. But that's not going to happen to us here. So you run the thing, it runs very fast, and here it efficiently finds the X's mark the center of the clusters, and the colored regions mark the dots that are sorted into these clusters. And as you can see, it did a very good job of sorting into these 5 groups. So to see how it works, we're going to run this one, which just shows the first 3 iterations of it, because it is incredibly simple. And that's why it's been around so long. It doesn't take very much computing resources to do it. So what you do, this should come up within a few seconds. Okay, first you just pick random locations for the 5 centroids. And then the algorithm is draw a border between them, take all the ones associated with this centroid, calculate the center of those dots, and move the centroid to that. So this one moves down a little. This one is going to move over to this dense pack of dots. This one's going to move over into those dense pack of dots. You can see it here. Yeah, this one moved. This one here will move up closer to the center. This moves closer to the center, and that's it. You move it to the center, and then you repeat. You draw the boundaries between them again, and now you move to the center of the dots associated with you. And so, as you can see, this one here that was really wrong will move towards the center, and then it will move towards the center and towards the center, and so will this one. You look at the one on the right, it's here, it moves to the right, it moves to the right again. This is extremely effective. If your data is in fact clustered in groups that don't overlap too much and that get denser towards the middle, then this will just naturally converge to a solution. It's very simple. All right, yeah, and k-means plus plus, yeah, is one that recalculates better conditions. Good. Anyway, so that's k-means. That's what it does. And it's quite effective. And now we can see, I think, examples. If we change the random seed to 2, then we'll have bad luck. I just tried random seeds till I found one that failed, of course. But if we change it to 2, then it's going to get different random starting values. And you'll see if the random starting values are way off, like here, see it put 3 dots over here and only 2 over there. So now that it's got such a bad start, these are both going to try and find converging areas here, and this one is going to just hit between these 2 tight clusters, so you're going to end up with a bad sorting. These 2 merge together and this one split into 2. So that's what I mean. If you have a bad enough starting value, it will not converge to the best solution, but it will find a less perfect solution. And by the way, there is a score here, which is the negative mean squared error, distance between the centroid and the dots. And so a number closer to 0 is better. So minus 211, that's a good fit. And this is minus 300 or 220, that's a bad fit. The total of the squared distances to the centroids of the dots is bigger than it should be, primarily because of this right here. Instead of having 2 centroids in the center of each region, you got one in the middle, so there's a bunch of dots that are further away. All right, so that's what can happen if you have bad starting values. That's why, by default, it tries it 10 times and chooses the best, so it has 10 chances to get a good starting value. And also, it has a problem with scaling, just like quite a few of these models. Like I say, this is why you normalize things. So if I do this, I will create, the original data is in X, and now I'm going to create X expanded underscore exp, which is going to be multiplied by 10. So here, the x1 range is minus 1, 0, 1, and this is 1, 2, 3. So you see they're pretty much comparable. The whole scale here is about 2, and the whole scale here is about 4. So the two ranges are approximately equal. But now I'm going to multiply the vertical one by 10. So it's the same pattern of dots, but this is now going up by 10s when this is going up by 1s. And that is going to foul everything up. If we fit a K-Leans model to this one, then now it's going to break it up this way, which is pretty terrible. Remember, the problem is now vertical distances count 10 times as much as horizontal distances. So it's willing to accept these dots being way over here, but not willing to accept any vertical dispersion. So the optimal solution would no longer be to put up a center here and a center here, because that would include a whole lot of vertical dispersion, which is really bad. So this is probably the mathematical correct solution now, but that's because just this scaling factor has changed this measure of success in such a way that it doesn't really measure what we meant by success. And that's why I say you have to normalize models, or you have to think about it. If you're going to have one scale 10 times bigger than the other, you have to really believe and mean that this is 10 times more important than the other. In this case, the dots are nice symmetric circles, and so you really want it to hit them in symmetric ways. That means you want the scales to be equal. So that's a thing to know about. Like a lot of them, it can't handle misscaling. And now if we try something that has a more complicated relationship, like the moons, then this is something that is kind of hard to see. It doesn't have any ability to make a weird shape to the cluster. It can't put the center here and somehow skew it to follow this shape. So you could say K-means isn't good at this, and the textbook says K-means failed. I really didn't feel like it failed that much. As you can see, there's instructions here how to fit it. I was able to fit it with something like this, and in my opinion, this is not bad. You would just add another layer that says, I want to combine these 4 groups into A and these 4 groups into B. It seems to me like this actually is pretty good, although by itself, it did split it into 8 groups, not 2. But the 8 groups are not bad if you then combine them. Anyway, that's obviously, this is what it does. It can only do blobs of dots that are near each other. And so we're going to use clustering for semi-supervised learning now. And let me do this. I think I'll just keep going with the same one. All right, so now we're going to switch from the moon shapes, dots and such. We're going to switch to those digits, handwritten digits. Okay, there they are. And here is the first 50 handwritten digits. And now what we're going to do is we're going to do semi-supervised learning. This is pretty awesome. We have the actual right answer for all these digits, but pretend we didn't. Pretend all we had was the images and nobody had already labeled them for us. So we have to label them, and we don't want to bother labeling 70,000 images. So you can label the first 50 by hand. That's pretty easy. So suppose you label only some of them. Now here we're going to do we're going to fit a model to the training set, a logistic regression, and then we're going to But this is the kind of model that you could get if you use the labels. Let's start with that for comparison. And we've done this before. So if you use all the labels and fit it to the entire training set, which in this case is 1,400 images. This is not, I think, the MNIST, it's another one, the same thing. So we get 90.6% accurate. Right. So, all right. Now, if we fit a model to only 50 images instead of the 1,400, then logically you would expect your model to be less successful if you used less of the data to train it. So let's see that. Now it's only 74% accurate. So that's much less accurate. All right. But the point is, we chose the first 50 images, and those 50 images are not really the best. Like if you look at these first 50, you can see the twos are kind of blurry and bent. There's only a few nines, and some of these nines are really pretty distorted. So it appears that just choosing the first 50 images, we didn't really get the best images to prove as exemplars of the images. We might have gotten messed up ones, and so the model has learned a poor method of discriminating between them. But if we could pick the best images, the best, most representative images, and train on them, that would be better. And that's why you combine unsupervised and supervised learning to do it. We're going to cluster the images using k-means into similar images, and then find the images in the center of the clusters, and those are the truly representative images, and then we're going to label them and use them. That's the trick, which is pretty brilliant. So we use k-means to form 50 clusters, because we observed there's several different ways to draw a 9 and a 7, so we're going to let it have on average 5 different shapes for each of those 10 images. We're going to sort it into 50 clusters with k-means. All right. All right, and now these are the representative digits, the ones near the center. And notice they're much nicer. The 9 is better, much less distorted. These are better models to train on. These are the centers of all the clusters. So now we're going to manually label them because they're chosen from random locations, and I've already done it, 1360, and you can see here they are, 1360. So you manually label just 50, and now you project those labels on all the others in the clusters. All the ones in the same cluster just inherit the label. Let's see if that's right. No, well, we're just going to train on just those 50 right now. We'll do that other thing later. So now we're going to train on this 50 instead of on just the first 50. And now we get up to 84%. And before we were in the 70s. We were at 75%. But we've gotten up to 85% now by choosing the most representative images to train on. So that's good, but we can do even better. We can propagate the labels to all the instances. We now have 50 clusters, and we know we labeled the center of the cluster, so we're just going to say everything else in that cluster has the same label as the thing in the center. So we propagate the labels to all the instances and train from that. So this is semi-supervised learning. We only had to label a small number of images, and now we can synthetically create a fully labeled data set and use supervised learning based on that. And this was 84% right. And this is now 89% right. So it's getting pretty well, getting pretty good. And now we can do one more thing. We can take away the outliers. Remember the unsupervised learning, we can have the clusters, and we can find the instances that are far from the center of the cluster and decide those must be the digits that are scrawled and pretty nasty. And we really shouldn't train on them at all because they're the ones that are messed up. So we're going to take the ones that are the 1% that are furthest from the centroids. We're going to keep the 99% near the center of the clusters, but remove 1% of the images that are not fitting in any cluster very well. We have now found images that are probably the messed up ones. And after removing them and training on what's left, we get up to 90.9%. And that's very good. That's as good as the training using the original labeled training set. And it occurs to me, I didn't do it, but it would be kind of fun to find the ones we threw away and display them so we can see. I would assume they're the most distorted, messed up images, but it's sort of fun to see them. Anyway, there's a couple flags to get here, and these can be a little tricky to do. You have to do quite a few steps of adjusting things. And there was one thing that got some students stuck was up here. Yeah, here you change some numbers and then make sure you're using the original data, not the scaled data that goes up by tens, or of course everything will be very different. Anyway, so that's k-means, a very powerful technique, and it's also has this interesting interaction between unsupervised and supervised learning, where you cluster it and now you label the clusters. So that's a lot of good tricks to know. I'm stopping this recording.